Welcome to Ask and Learn.
In this question, we are asked to show that every totally ordered set is a lattice. So a lattice is defined as a partially ordered set such that any pair, when we look at any pair in the set, like these two, the set will have the least upper bound and greatest lower bound. So these two, I believe you should know the definition, but I will just repeat it. So upper bound is any element that is like greater than everything in the set, right? But the least upper bound is the smallest such element. So the least upper bound will be the smallest among like any other upper bound, and that can only be one of them. Similarly, greatest lower bound is lower bound is element such that it is less than everything in the set. Greatest lower bound is the largest such element. So, and there can only be one. Okay? Lattice, opposite will be a lattice if any set of two elements like this, any pair that we choose, has both least upper bound and greatest lower bound. And so, let's prove this. Let A be a totally ordered set. So it is obvious by definition that A must be poset as well, partially ordered set, right? Because totally ordered is like stronger than being partially ordered. And now consider a set of two elements from this totally ordered set. These two, since X and Y are both in A, and A is a totally ordered set, we must be able to compare them always. So what will happen is either X is less than Y or Y is less than X. One of these has to happen. And without the loss of generality, we can always change the name of these two elements so that we have X less than or equal to Y. Okay, there is nothing complicated going on. We just say that, oh, we can always label them in such a way that Y is the greater one. Okay, just renaming things. Now, when this happens, it means, oh, and I'm gonna claim that then Y will be the least upper bound and X will be the greatest lower bound of this pair. Why? Well, first Y is upper bound. This is clear, right? Because Y is greater than X and Y is greater than or equal to itself. So Y is definitely upper bound. But Y is the least one because any other upper bound, suppose Z is upper bound, we cannot have Z less than or equal to Y. No, I should say Z strictly less than Y. Why this can happen? Well, if Z is less than Y, then Z cannot be upper bound anymore, right? We need Z to be at least Y because Y is an element in the set. Okay? When this can happen, it means that Y is the least of them all, the least upper bound. And by similar logic, X is lower bound by default, but X is the greatest one of them. There is no lower bound that can be greater than X because it will no longer be upper bound. It will no longer be a lower bound at that point. Okay, so let me just say this. No upper bound can be less than y. So it can go at most equal to y. Okay, and the same thing with x. So we just show that when we start with this pair of element x and y, we must be able to compare them. And once we compare them, the bigger one will be the least upper bound. The smaller one will be the greatest lower bound. Okay? We can always do this in a totally ordered set. That means the set A is actually a lattice because it fulfills the two conditions. It is poset. We can find the upper lower bound. And that is it for this video. Thank you.